Dear students, let us continue our video lectures on Advanced Digital Signal Processing course. I am sharing the screen. In this video lecture, let us discuss the details of filter design. So as we were discussing in some of the previous lectures, designing of filters makes an important system design in analyzing the signal processing, signals and systems, and also during signal processing. Okay, so what does a filter indicate is, say if we have some input signal that is given as x of n to a system with impulse response h of n, the expected output is y of n. Usually in some of the signal processing tasks, we know a priori what is the signal processing task that is to be done. Say in the given signal x of n, I may be interested in a particular range of frequencies to be enhanced or a particular range of frequencies to be attenuated. To give you an example, say I have a signal like this. So x of n is equal to cos. Okay, so let me give a discrete signal since I started with discrete signal. Okay, 2 pi by 3 into n plus cos pi by 3 into n is the signal. Okay, in which what I expect to get in the output is, okay, only the term that is cos pi by 3 into n. Okay, assume that I don't wish to have the additional term that is this in the output of the signal y of n. So I expect the x of n to have only cos pi by 3 into n. In that case, so if you analyze this in frequency domain, you can see that there are two frequencies present in the signal. One is at pi by 3 and another is at 2 pi by 3. So I should pass pi by 3. So if I sketch the spectrum of this, okay, so discrete time for a transform of this x of n, okay, in omega. So how does it look like at pi by 3, okay, and minus pi by 3, okay, minus pi by 3 and pi by 3, I may have two impulses of height half. Similarly, I may also have at minus 2 pi by 3 and plus 2 pi by 3. Another two impulses okay, minus 2 pi by 3 and plus 2 pi by 3 and 2 pi by 3. And this is 3 pi by 3 in some sense. Okay, assume that this is 3 pi by 3 and hence this is pi. Okay, so and then this is minus pi. So this is the range of the spectrum, right? Minus pi to pi range of the spectrum. Okay. One cycle of discrete time for a transform, okay, of the signal x of n. Each are of, so this is x of e power j omega. Okay, so minus pi to pi. Okay, so now you can see that there are two cosine signals or cosine signals with two different frequencies are mixed up, and the expected output, let it be y e power j omega. What I wish to get is does have only one specific cosine signal. Okay, so that is this. Okay, this is at minus pi by 3 and pi by 3. So if I wish this to happen, what should I have? Ideally, I should have a filter here. Okay, that filter has to be, so ideally I should have a filter of height, okay, of height 1, and that passes only one component of among these two cosine signals. Okay, so that's what will happen. This filter height here is 1 and filter height in this region say is 0. That means, say let this be up to this frequency, that is, say if I mm, minus pi, say this is pi by sorry, pi by 3, right? Okay, and based on this we can write this as uh, pi by 6 into 4 pi by 6. Okay, this 4 pi by 6. Similarly, minus 4 pi by 6 will be here. Okay, so we will like the exact cutoff frequencies are up to where this has to have a filter has to pass, and after which the filter has to attenuate, we can decide later. Okay, we will see how to design them later. But the idea here we are trying to convey is to some of the signal processing operations are mainly driven by filtering operations. That means in the frequency domain, okay, so in the frequency domain, say if I have from minus pi to pi, minus pi to pi, I may wish to pass some of the frequencies, I may wish to attenuate some of the frequencies. Okay, right. So this is one kind of filter, wherein the filter passes some frequencies and attenuates some other frequencies. This passes which frequencies here? Based on the frequencies which the filter passes, it is referred to as low pass filter or high pass filter or band pass filter. Okay, so here if you can see the frequencies near to 0 in discrete domain, we consider them as low frequencies, and those are close to pi or high frequencies because of their nature of the the oscillations that they generate in the corresponding time domain signal. Okay, so and hence this is a low pass filter. This is ideal low pass filter. Okay, so this is referred to as cutoff frequency, up to where it passes the signal without much attenuation, and after which it attenuates the signal. That cutoff of the frequencies is referred to as cutoff frequency. Okay, cutoff frequency distinguishes between the pass band and the stop band of the filter. Okay, what we are discussing here is about ideal frequency selective filters. Okay, so we are trying to see how does the ideal frequency selective filters look like, and later we will see how to design them. Okay, so now as a general case, we may have an x of n that is equal to, say, some original like the desired x of n, okay, plus a noise added, right? See, what may happen is in a communication channel, if there is a communication channel, this is for an example, a practical example. Okay, I may initially might have sent the desired signal to be transmitted, but at the output of this channel, what I may have is xd of n added with, okay, the noise through the channel. Okay, so this may be a channel adding additive noise to the signal xd of n, right? That may be the effect of the channel. That may be due to thermal effects or like random noise perturbations in the signal through while transmission and so on. Now, while designing the systems, what we do in signal processing is to design a inverse system for this. Inverse system is here noise got added, okay, through the channel. This is channel noise. Okay, this can also assume that for time being, this may be frequency selective noise. That means channel adds only noise of some particular frequencies. Okay, so usually say for simplicity, noise frequencies of this noise, okay, are greater than some omega c. Okay, noise frequencies are greater than omega c, and the signal frequencies, okay, are roughly, okay, less than omega c. Okay, it may not be possible in all the real cases that the channel noise frequencies and the signal frequencies will be different, but they can be like, there may be some overlapping regions for both of them. However, the dominant frequencies of the channel may be of a high frequencies, channel noise may be high frequencies, while the signal may be low frequencies, because many of the natural signals are of low frequency, are known to be low frequency, because they are smooth most of the times. Okay, and this is the impulse response of the filter. Now we wish to design what is its job of the filter. You get here y of n, fine, but this y of n has to be equal to xd of n in some sense. Okay, that means it has to suppress the noise, that is eta of n. Okay, so as a simpler example, you can consider xt of n plus, okay, this cos, okay, 2 pi by 3 into n. This is a just simplified example, but you can consider this output signal is added with the desired signal plus a frequency selective noise. Okay, so in that case, you can easily see the above, connect to the above scenario, wherein you can design a filter that separates this, that suppresses this frequency. Okay, this frequency gets suppressed by filtering. Okay, that's what we are trying to do, right? Okay, so this is an ideal low pass filter. So what do you think are the other kind of frequency selective filters that we wish to discuss? Okay, so in sometimes, see, the signal may be of high frequency and the noise may be of low frequency. This is very rare cases, but still it may happen. So x of n, okay, of high frequency, and h of n, okay, and so high frequency, desired x of n is high frequency, but x of n, given x of n is mix of high and low frequencies. High frequency signal plus, okay, low frequency noise. Okay, it's rare chances, but we assume that such a situation exists. Then the filter h of e power j omega, that is the frequency of the response of the filter, ideally should be something like this. Okay, it suppresses the high frequencies. It passes the high frequencies, suppresses the low frequencies. So, see, please note that the discrete frequencies is what we are looking here. Okay, and they range only from minus pi to pi. Okay, whereas the most of the specifications are given in continuous time domain. Okay, and hence the continuous frequencies also are important factors that are specified for the filter design. We will see how to convert the specifications given in continuous domain for the frequency spectrums to convert them to discrete domain for designing these filters. Many of the filter design happen in discrete domain because of the advantages it has for realizing through computer. Okay, so finally, filter may be just an operational algorithm, computational algorithm, okay, that processes the signal in computer, or a small hardware that processes a discrete signal. Okay, so these discrete filters. So we discuss more in this video lecture on the discrete filter design. However, as I said, the specifications are in continuous time, and hence we will see the relation between bringing the continuous time specifications to discrete time specifications and then design the filters in discrete time. Okay. Okay, so this is high pass filter because it passes high frequencies. Okay, and here the magnitude is 1 and here it is anyway at 0. This is ideal. Ideal high pass filter again. They're all ideal filters. We will see why we are calling them as ideal. Okay. So now what may be the other possibility of the requirement of the filters? So you may have band pass filters or band stop filters. So if you see this, this is a band pass filter. Okay, your minus pi may be here. Okay, and pi may be here. Okay, and passes certain frequencies. This is band pass filter. Ideal band pass filter. See, to give specifications, here you need only one cutoff frequency that changes from, okay, stop band here to pass band. Whereas here, how many specifications are required? This is now pass band, where it passes without much attenuation. The frequencies are passed without much attenuation of the input signal, and this is stop band. And is there only one stop band here? There are two stop bands. In fact, three stop bands. See, most of the time I am sketching the symmetric filters. Frequency domain representation of these filters, if you see, they're all symmetric. Can you tell what may be the reason why I'm all sketching all through the symmetric filters only? The reason being the symmetricity in the frequency domain is ensured. That means by the real coefficients of the h of n. Okay, most of the times we prefer to realize the filters through real coefficients in h of n. So if h of n has, okay, h of n has real coefficients, okay, h of n has real coefficients or samples, h of n is real, implies that h of e power j omega magnitude spectrum is symmetric. Please note how we are using the properties of the Fourier transforms here. Okay, that's how they will be used at several places. Okay, assuming that you are all comfortable. Okay, so you should make sure that the properties are well understood and can be applied at any time. So now assume that we again put here, assume that this is ideal band pass filter, right? So the other possibility is to have a band stop filter. It may stop only particular frequencies. Okay, this is a band stop filter. Please note that all through we sketch from minus pi to pi because this is a discrete time Fourier transform and periodic with 2 pi. Okay, and you know that this is stop band. So to make the specifications of this ideal band pass filter or okay band stop filter. Band stop. Okay, what are the specifications to be given is the pass band. Okay, first pass band, we may say that there are here okay only one pass band, so WC1, WC2. Okay, cutoff frequency 1, cutoff frequency 2. Similarly here, okay, cutoff frequency 1 and cutoff frequency 2. But based on the band pass or band stop, okay, the region between W1 and WC1 and WC2 changes. Similarly, okay, this discussion is all for ideal filters. Okay, we will see for in practical cases, can we realize this ideal filters? Okay, or are there any modifications that happen, or even will there be any change in the specifications now? Okay, these are all the different kind of filters. High pass and band stop filters. Okay, right? Fine. So let us consider the ideal filter. Okay, ideal low pass filter. With respect to low pass filter, we will discuss. We will make the discussion now, and the same discussion will extend to other design of high pass, band pass, or band stop filters. Okay, fine. So there are other kind of filters. Say for example, the other one, like important filter people usually use is notch filter. Okay, notch filter is the one which passes only particular frequency. Okay, in fact it's even narrow than which I have plotted here. Okay, so assume that it is like this. So it just passes a particular frequency. Okay, so please make sure that we are making the real coefficients for the design considerations, because the number of multipliers for the real h of n for realization of real h of n will be much lesser than complex h of n. Okay, so and hence this is a notch filter. It may pass only particular frequency, or it may stop only particular frequency. Okay, so it may pass every frequency and may just stop this frequency. Okay, this is also possible. Minus pi to pi. Okay, this just stops this frequency. Okay, so this is also notch filter. Okay, fine. So fine. So let us see now design of low pass filter. What are the problem? Okay, in short, we write as low pass filter like this. Okay, so ideal low pass filter we have discussed before. So please note that whenever I put a filter here, okay, there is a system that is underlying this. Okay, minus omega c to omega c. Okay, and then anyway pi and minus pi, all those things. Okay, and this is in fact h of e power j omega. For now, let us not discuss more on the like phase aspects of this filter design or filters. Okay, later we will discuss like when appropriate discussions come, we will discuss more on phase, but mostly what we will be discussing on the magnitude spectrum. Okay, we would like to pass certain frequencies in the magnitude spectrum of the like this filter Fourier transform of the filters. Okay, so magnitude spectrum of the signal. We want to like attenuate or pass, and the filter design is mainly now guided by this magnitude spectrum. However, the phase also has some consequences and important role to play when designing the filters that we will discuss later, or as and when the respective discussions come. Okay, so now x of n if we give, and this is in some sense h of e power j omega, what we get is y of n. Okay, having only the frequencies that are passed by the filter. Okay, that's what happens. Fine. Only minus omega c to omega c frequencies of x of n that are there in x of n. Okay, right. Okay, so now let us see. You say assume that you wish to design such a filter. Can you please tell what will be the time domain impulse response of this filter h of e power j omega given by this? So if you recall, this is a like rectangular spectrum, and then in the time domain, what we have is a sinc sine omega c into n by pi n. Okay, so this is what is the frequent like time domain impulse response corresponding to this given h of e power j omega. The low pass filter at cutoff frequency of omega c. Okay, that is h of e power j omega has in discrete time Fourier transform inverse dtft gives us this h of n. Okay, right. So now see if this h of n is like this, do you think can we realize this? Can we realize a system with this impulse response? Say h of n is in fact a I am just sketching this spectrum here. Okay. Okay. So let us assume that this is the impulse response. Okay, but please note that this is a discrete time impulse response. So ideally what you have are these. Okay, as I am just sketching at some points. Okay, and so on. Can you please see from where to where this impulse response extends to? This impulse response extends from minus infinity to plus infinity. Okay, even though this is 0, okay, for n axis, discrete time axis, and it extends from minus infinity to infinity. The question now is, can we realize this system? First of all, is this impulse response, say if we have a system corresponding with this impulse response, okay, what is the nature of the system? Say if we have a system with this h of n, okay, what is the nature of the system? And this is a low pass filter, okay, corresponding to this. Okay, and what is the nature of the system? The system is this causal? Okay, the answer is no, not a causal system. So can we realize this? The answer is no. So we cannot realize. Okay, this first thing. Second thing is Is this a finite impulse response or an infinite impulse response? This is infinite impulse response. Okay, so it extends from minus infinity to infinity. But however, is this really needed to consider this h of n that is extending from minus infinity to infinity? Should we consider all the values of h of n to have a realistic approximate of this h of n in the time domain? Okay, the answer is no. Because see, ideally what I wish to have is only particular regions, okay, where there is a significant information in h of n. Okay, so it may be good enough for me, okay, to take the region that is, say, from I just put some value. Okay, so ideally it may be good enough for me to take from here to say 1 2 3 cycles, 1 2 3 cycles. Okay, from here to here. Please note. Okay. Okay. So the values later are very small and can be neglected. Okay, based on the importance of like the magnitude of the impulse response. Okay, we have. So if I take this region, which I have marked in as the region of interest in h of n, it is good enough to practically reproduce or realize this h of n. So no need to take infinite impulse response, and we have the provision to truncate it and take only the significant magnitudes of the impulse response h of n to realize the corresponding h of e power j omega, right? So this truncation is usually done through a window referred to as window function. Okay, so if we truncate them, then what we have? Truncated impulse response, okay, with significant magnitude of h of n is finite impulse, finite. Okay, and hence I can do finite impulse response. Okay, I can approximate it with finite impulse response system or FIR filter. Okay, so based on how I realize the filter, there are two categories of filters. One is referred to as FIR filters, the other is referred to as IAR filter. Okay, if I do not truncate, if I directly realize them, what I refer that as, okay, the infinite impulse response or IIR, infinite impulse response filter, to have all terms in h of n. Okay, so we may have here, based on this discussion, we may have FIR filters or IAR filters. Okay, for given h of j, given h of e power j omega. Okay, and h of n correspondingly. Okay, for this we may realize through as a finite impulse response filter or infinite impulse response filter. Okay, so now let us first consider the realization of finite impulse response filter. Okay, So let us discuss on FIR filter design. Okay, so where did we start? We said we have actually a system with us. Okay, X of n as input, and we want a filter, and this filter should only pass low frequencies. Okay, and like the attenuate the high frequencies. This will have h of e power j omega, and the sketch of h of e power j omega, if we see, looks like a low pass filter. It is a low pass filter. Okay, so it passes some frequencies. Okay, the magnitude I maybe keep changing from omega c to omega c. Okay, and then it attenuates the rest of the frequencies. Okay, so it just passes them. Okay, so this is the ideal low pass filter. Filter that is h of e power j omega, magnitude of h of e power j omega. This we get from this. Okay, right. So now what we have seen is in the time domain, if we just take this into the time domain, okay, we have seen that we get h of n, and this looks like a extends from minus infinity to infinity, and we thought of truncating it to have a finite impulse response filter. Okay, so assume that the truncation is done. See what I plot here now. See, truncation is done through an operation of multiplying the impulse response with a window function. Okay, W of n. So the desired impulse response is what I have got here. This is the desired frequency response, and from that I got desired impulse response. Okay, so but for the practical reasons, as I said, we may not be able to get the desired impulse response. We multiply this desired impulse response with a window function, W of n. Okay, and this multiplication happens in time domain. Please note that. After that, what we have is truncated. Okay, truncated impulse response. Okay, let me try to sketch it. Okay, we have exactly we may not be able to reproduce, but let us see. Okay, so let this be the filter we wish to design, and this is the truncated filter. Okay, truncated impulse response. I think I skipped one line here. Okay, let us just make it. It is, in fact, it has to be symmetric. So let me see if I can make that symmetric. Right. Okay, so let us let this be the truncated impulse response. Okay. Now the question here is, if we do this truncation, now the impulse response is say minus some value to plus some value. Okay, but the thing is this still a causal system or not? Because if you want to realize them through hardware, you need y of n, okay, as anyway convolution sum of h of n and x of n, and this should depend only on x of n, okay, terms of x of n minus n naught, where n naught is positive, okay, n naught is greater than 0. In case if n naught is less than 0, it means that it depends upon y of n depends upon future inputs. Okay, for this to happen, what should be the nature of h of n for causal system? Okay, n greater than 0, this is for causal system. Okay, so please note that this condition is for causal system, and the question here is, what is that imply on the h of n for a causal system? No, if you recall our discussions earlier, for a causal system, okay, h of n has to be 0 for all n less than 0. Okay, but the question here is, if I truncate them now with say all with all n less than 0, so if I truncate like this, okay, even up to here, okay, do you think is it a better way of truncating the impulse response hd of n? Does it really look like the original hd of n after truncation? The answer is no, so I will not be able to truncate like that. So for practical design as purposes, what I do is I shift the impulse response, this truncated impulse response. So what I say is, the desired impulse response itself, okay, doesn't start from 0, it starts from some value here. Okay, I will shift the location of the desired impulse response. So I say for the desired impulse response, 0 is here. Okay, assume that I may start from here. Okay, and then this ends here. So this is the final value of the impulse response. So this is 0, 1, 2, and so on. Okay, and this is some value, and this let be m. Okay, so if the impulse response for realizable or causal hd of n, okay, this is the modified version of hd of n. Okay, so it starts from like I we delay the impulse response of hd of n to make this realizable, such that the peak of the hd of n, okay, the sinc function comes roughly at m by 2. Okay, this comes roughly at m by 2. Fine. So that actually what we can do, we can easily realize such the corresponding system h that we wish to realize as a filter is causal. Okay, and now this hd of n, now if I write with this delay, so how much delay I did to this? Say hd, I will write causal, hdc, causal desired response. Okay, let me write with some notation. Fine. So let me write this as, okay, hcd of n, causal desired response, is equal to hd of n minus n naught. So, but how much should I delay? Roughly equal to m by 2. Assume that I delayed by m by 2. Okay, assume that here m is length of the filter. M is the where, okay, m is length of filter, means practical filter. Okay, that is impulse response of the filter. Okay, or in the desired impulse response, what are the significant terms? Okay, m by 2 significant terms only we consider either side. Okay, so or considering m by 2 significant terms in desired impulse response of filter. okay, or HD of n. Fine. Okay, so considering this, we have this H realizable or causal is this. Okay, and hence now given this scaling, the window function now W of n we can define as 1 for 0 less than or equal to n less than or equal to m and 0 else. And h of n, okay, that finally our h of n is obtained by HCD of n causal desired response multiplied by W of n. Okay, so when we define this W of n equal to 1 for 0 to m, we multiply for the causal desired response rather than the original desired response to get h of n. Okay, so if we define like this, okay, then what we see is W of n is minus m, but whole thing we need to delay. Okay, so for practical reasons, we assume this. Fine. The another question is, see, we are doing all these operations fine to make a realizable filter and to approximate the filter impulse response by finite impulse response, like through a finite duration. However, we need to see if we do all these modifications, that is shifting in time domain by m by 2, considering m by 2 significant terms of the h of n, hd of n, and multiplying with w of n to make this finite. Okay, two operations we are doing. One is to make the realizable filter, that is causal. Okay, so if you see, these are the two operations. Okay, one is to make the realizable filter, that is causal. Second is the windowing operation. Okay, that is to make the finite impulse response. For making h of n finite. Okay, so when we do these operations, we need to see what are all these implications in the frequency domain. Because finally, what we wish to do is, how does this filter look like in frequency domain? Okay, how do we design a effective filter in frequency domain for selecting certain frequencies or passing certain frequencies and attenuating certain other frequencies? Okay, so now let us see. So, right? So let us see now in the frequency domain, what are the implications of this? So to summarize, we have done two operations. So I will write now. Hd of n is equal to h of n, h desired n minus m by 2. Okay, this is the first operation. Delaying for making a causal filter. Okay, for making causal filter. Second operation is h of n, we obtain the impulse response of the filter is a CD of n multiplied by Wn, windowing for finite impulse response. Okay, for making finite impulse response. Fine. So what we have initially was, so hd of n has its h of e power j omega through discrete Fourier transform, discrete time Fourier transform, okay, gives us, okay, hd of e power j omega, which we have seen as this spectrum. Okay, I am just sketching minus omega c to omega c. Okay, and let it be minus pi and this be pi. Okay, so now the question is, see, first operation. So if we do first operation, okay, that is first operation, h CD of n, if we do, okay, what will be the dt of t, which is equal to hd of n minus n by 2. We delay by, if we delay by m by 2, what is its implication in the frequency domain? Can one of you tell? So this, when we define, this is equal to, okay, when we define this h of e power j omega, okay, ideally we are considering, assume that 0 phase, okay, 1 for mod omega less than or equal to omega c, 0 else. Okay, assume that initially the desired response we had was 0 phase, okay, and 0 phase, and magnitude as shown here. Now, due to this change, what will happen? HCD of e power j omega now is equal to HD of e power j omega into, what will happen? N minus this will be e power minus j m by 2 into omega, right? Omega into m by 2. So there is a phase change that occurs. And when we expand this, how does this look like? E power minus j omega m by 2 for mod omega less than or equal to omega c and 0 else, right? This is for HCD of e power j omega. So what essentially, if I sketch it, the magnitude spectrum is unaltered, while the phase spectrum will have a term, modulation term, e power minus j omega m by 2. The delay in time domain reflects as phase delay. Okay, that's only the change because of the first step we have taken for the desired response. Okay, so all through in our low pass filter realizations, if we wish to make a causal filter, we should define the desired impulse response as this, okay, as this rather than this. Okay, if you wish to design a causal impulse response, this is the ideal impulse response of the filter or frequency response of the filter, and not this. Okay, if for it non-causal, this is fine, but for causal you should have a delay in the frequency response. Okay, or the phase delay in the frequency response. Okay, fine. So this is the first consequence, and hence what you observe is we redefine the ideal desire or the desired frequency response. Okay, the magnitude spectrum is unaltered while the phase spectrum is this, given by this. Okay, now let us see the consequence of second step. Okay, we multiply by window function. So h of n now, the filter finally we design is equal to hcd of e power hd of n multiplied by window of n. And in frequency domain, if you take discrete time for a transform, okay, what will happen? This h of e power j omega that we will be designing or finally wish to a practical filter of frequency response is equal to the causal desired frequency response convolved with the window function frequency response. Okay, so now the question is, how does the window function frequency response look? Okay, so can you tell what will be w e power j omega? This is, see, w of n, as you have seen, okay, of n is defined like this. Okay, it's a rectangular function purely, 0 to m it is 1 and 0 elsewhere. Now if you find w e power j omega, okay, I will leave it as an exercise for you to find. I directly write the answer here. Okay, so the answer here is, okay, let me write the answer here. E power minus j omega m by 2, okay, sine omega into m plus 1 by 2 by sine omega by 2. Okay, please verify this. But this looks like this is a sync function. Okay, in the this is a sync function in the frequency domain. Okay, if you sketch it now, the windowed frequency response. Okay, so frequency response of the window function, then it is a sync function. Sorry. And what is its length? Please note, its length is, its duration of this is minus pi to pi in frequency domain, because all the discrete time Fourier transforms extend over minus pi to pi. Okay, so assume that our minus pi to pi is up to here, minus pi to pi. Okay, okay, right? And this is 0 in frequency domain. Please note that this is mod of w e power j omega. So now what essentially happens to the practical filter frequency response? So now the question is, how will this be? Okay, because of this w e power j omega, okay, and this hdf e power j omega, okay, how does this h of e power j omega look like? Is our question. Okay, right. So now let us see that. Okay, right, let us see that, because that's what practically we will be designing the filter. Our filter design will be, okay, instead of the ideal filter, because of the limitations of the causality we need and the truncation we have done for designing it as FIR filter. Okay, so the effect of these two will give us a practically designable filter. Okay, right, let us see that. So I will not mark now the exact things, but you can see from this expression where this, okay, where the like zero crossings are and so on. Okay, right. Yeah, we can even mark it. So what will be? So this has to be pi, where it first crosses 0 is pi. So this is equal to omega m plus 1 by 2 is pi, and 2 pi by, this is equal to 2 pi by m plus 1. Okay, and this is minus 2 pi by m plus 1. And this is what? This what location? 4 pi by m plus 1. Sorry, m plus 1 here. Okay. I don't know what disturb something. Okay, let leave it. Okay, so that's how the locations of zero crossings will be. Okay, so the length of the filter here, please note that the length of the filter, okay, the number of non-zero coefficients I take in h of n, h desired of n, will influence the window length, and also it will influence the the frequency response of the window. Okay, and hence it does in turn gives the practical filter frequency response. Okay, fine. But now if we will sketch it, you can see that this is the magnitude spectrum of the filter, and this is the magnitude spectrum of the window function. Now the question is, if I now make a convolution between these two, how will be the h of e power j omega look like? Okay, so let us see that. So let me sketch quickly. This is the ideal filter frequency response. So now let us take event to 0. minus omega c and omega c. Okay, let the filter be up to this. Okay, omega c, and this is pi, and this is minus pi. Okay, and this is the low pass filter. So the phase here is e power minus j omega m by 2. Okay, I'm just writing the phase as well. Magnitude is anyway, you know. Okay, so this is the h of e power j omega, h desired causal desired impulse response, frequency response. It should be convolved with, okay, this has to be convolved with what? This has to be convolved with the let me try to sketch 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6. Because minus pi to pi both extends minus pi to pi. Both are periodic and discrete time Fourier transforms. What I'm sketching here is, okay, window function e power j omega, frequency response of the window function. That is extending from 0 to 1, 0 to m, and 0 elsewhere in time domain. Okay, so how does this look like? So let us sketch with a lighter color. Okay. Okay. Similarly, this side. Okay. So yeah, let this be. Okay, I think it has gone up. Oh. Okay. So this be the W e power j omega. Okay. Now the question is, if I convolve these two, okay, if I do convolution of these two, how will be the let me sketch here, 0, 3, 3 minus pi and pi. Okay, so we have selected omega c, minus omega c and omega c here. Okay, now this is the ideal filter. I will now sketch the ideal filter with dots. 2, 3, 4, 5. Okay, 2, 3, 4, 5. Okay, yeah, and then okay, right, this is the ideal filter. Okay, now if we perform convolution operation, okay, what does it happen? This will keep convolving here. Please note that this keeps like this starts from, say, this gets flipped because of the symmetric nature. It doesn't matter whether if we flip this or not, and assume that now I start sliding it from infinity. Okay, so assume, see, infinity is not considered here, so minus pi, we start sliding it from minus pi, and see there is at, if I put no this this 0. Okay, so if I put this at 0, okay, if I put this this at 0, there is maybe small overlap for these tails here. Because of this, small oscillations of this nature will start coming up. Okay, and the value keep increasing as this is referred to as, in this window function, this is referred to as main lobe. Okay, because this is the region where you have actually, okay, the most of the energy of this window function concentrated. Okay, and this is referred to as slide lobe. side lobes. Okay, here there is not much energy of the window function. Okay, so they still keep dying down in the side lobes. Okay, so now side lobes exist in both sides. Here also we have actually what we have are side lobes, right? And how much is the length of the main lobe? If we see, length of the main lobe extends from where to where? Minus 2 pi by m plus 1, okay, to 2 pi by m plus 1. The window that we are referring to is rectangular window. The reason being, okay, this is W of n for this is equal to 1 for 0 less than or equal to n less than or equal to m. Okay, 0 else. This is a filter. Okay, rectangular filter. Okay, so rectangular window. Fine. And this length now is 4 pi by m plus 1. What is m plus 1 here? M plus 1 is the uh, length of the filter. M is the length of the filter. Sorry, m plus 1 is the length of the filter, and m we refer to as order of the filter. Okay, we will see why it is order of the filter. For time being, you understand here that the m, like m plus 1 is the length of the filter. I should write filter. Okay, or the window, because the length of the window and filter are same. Because okay, we in the time domain, if you see, okay, we are truncating it. So that's the length of the filter and the order of the sorry, the length of the filter and the window are same in time domain. Please note that. Okay, and this is the width of the main lobe. Whatever you have seen here is the width of the main lobe. 4 pi by m, thus the width of the main lobe is equal to, so let me write somewhere to make this is equal to 4 pi by m plus 1 for rectangular window of length m. Okay, length m in time domain. Okay, the width of the main lobe in frequency domain is 4 pi by m plus 1. Please note that this is the this directly comes from the definition of the window function and its discrete time Fourier transform. Okay, definition of the window function. Okay, sorry, yeah, this definition of the window function and the corresponding frequency domain representation. It directly comes from that. Okay, fine. So now what will happen once this main lobe starts touching this filter where it is non-zero, okay, the desired frequency response, it starts increasing. The value of the convolution starts increasing. And then when this reaches like when this completely comes and sit here, okay, and starts sliding, this main lobe comes here and sits. Assume that when the zero is exactly here, it means that the half of main lobe is this side, okay, half of main lobe is this side. And at that point, if you slide further, the like these attenuations or main side lobes start coming in, and hence they keep again oscillating, okay, the frequency response. Fine. And then after when this again touches this, okay, the main lobe starts coming out, and hence the frequency response comes to fall down. So I will sketch here a rough sketch of how the frequency response of the convolution, these two looks like. please see if you can understand from that. Okay, so again it will be symmetric, and this sorry, I think let me retry. Let me redraw. So right. So as you can see here, the oscillations start like the oscillations are because of the side lobes, okay, and the height that it reaches is because of the main lobe. Okay, so when the main lobe starts has a high overlap region with respect to this, okay, what you get is this height. Okay, and how much the time it takes to transit from 0 to like 1 here depends upon the width of the main lobe, right? Because if the main lobe has more width, it slowly goes to 1, whereas if main lobe is very narrow, it suddenly goes to 1, right? As you can see in the convolution. Okay, so what ideally is happening here is this uh this okay uh this coming like this. Okay, so I am not sketching the overall, only one or two places I will sketch. Okay, so you can see. Okay, like this, fine. So this keep on like moving like this. Okay, so when it touches the main lobe at this location, you keep the there is a movement of the, say, in the practical filter h of e power j omega, you will reach from 0 to 1. Okay, you will be reaching here, okay, from 0 to, when it closes, this is complete overlap between this main lobe and this, it will be close to 1. When the overlap with the main lobe starts decreasing, it again goes to 0. Okay, so that's what that's how you can understand, right? So, and these oscillations now are the because of the side lobes. So here for the practical system, practical filter, you can see that though we wish to attain a uh, attain a zero, like attain complete zero frequency like attenuation here in this range. That means we don't want to pass any of the frequencies. However, we may pass because some like small frequencies in the stop band as well. Okay, in the practical design of the filter. Similarly, we may not be able to exactly pass with the like one like frequencies in the pass band, but we may again here as well may be able to pass. Okay, so with some uh, at like the oscillations around 1. So what we see is 1 minus delta and 1 plus delta may happen for the frequencies that we wish to pass in the pass band. So if for a practical filter, the specifications to be given are slightly different from the ideal filter. What specifications do we give? Or this 1 plus 1 plus or minus delta here, okay, of pass band, okay, that is pass band attenuation. How much attenuation shall we allow for the pass band? That is one thing, okay. So, and then the second thing is how much attenuation can we allow in the stop band, okay, 1 plus delta p. So, delta p is allowable, okay, pass band attenuation or oscillations around 1, okay, magnet 1 like around h of e power j omega, h desired e power j omega, okay. Similarly, we should be able to allow delta s. Delta s is allowable attenuation in stop band. See, ideally we wish to have complete attenuation in the stop band, and the magnitude of the frequency response has to be 1 in pass band. However, we for practical reasons, because of the windowing operation, we can only have the frequencies having an attenuation of less than delta s in the in the stop band, and around 1 minus or plus delta p in the pass band, okay. So this is maximum uh, attenuation deviating from 0 in the stop band and deviating from the pass band with respect to the 1, okay. So these two are the specifications in addition to the the ideal filter response to be given. Further, see, we may not exactly reach the stop band and the pass bands, okay, at omega c now. So because of this, what will happen? We may be reaching the omega c, okay, here, and we may be stop band here. So this is the pass band cutoff frequency, and this is the stop band cutoff frequency. So the stop band starts from omega s, whereas the pass band ends at omega s. Omega p, pass band, cutoff frequency. That means after which we have actually, so say omega p is frequency, is omega, okay, now less than or equal to omega, till which the attenuation is h of e power j omega is, okay, less than 1 plus delta p to 1 minus delta p. Let me write a little better. Okay, so such omega p is the pass band cutoff frequency, okay, in which this condition is valid. The frequency response is between 1 minus delta p to 1 plus delta p, or around 1, okay. Similarly, the w the stop band cutoff frequency ws is stop band cutoff frequency defined as, okay, in which what do we have? Mod of h of e power j omega is less than or equal to delta s, okay. So stop band attenuation, allowable attenuation in the stop band. So now these are the modified specifications for a digital practically realizable filter. Fine. Specifications for practical filter, digital or discrete filter. Okay, so these are the, and this is the filter response. Okay, this is what we are showing here is h of e power j omega. Okay, so what we have sketched is h of e power j omega, and then h of e power j omega is this magnitude plus the phase that is defined by e power minus j omega. Okay, so when we want to specify the specifications, these are to be given. You need to give. So in terms of specifications, you should tell, okay, omega p, the passband cutoff frequency, omega s, stop band cutoff frequency, the passband allowable like attenuation around 1, stop band attenuation around 0. Okay, so these are the 4 parameters to be specified for a practical filter design in discrete time domain. Okay, so now we will see a small example on how to convert the specifications of the continuous time filter to a discrete time filter. Okay, so this is the answer result of the convolution. Okay, please note that this is the result of convolution. Okay, if you do this convolution, what you get is this. Okay, fine. So as we have discussed here, the oscillations here are attributed to the oscillations of the side lobe, whereas the like the transition, this omega p to omega s is referred to as transition band. That is referred to the width of the main lobe. So I will show that more clearly here. Now let us sketch the practical filter. How does it look like? Okay, 0 here, and the practical filter here is okay. Okay, let this be a practical filter. Okay, so this is the practical filter that we can realize. Okay, so this is h of e power j omega. Okay, what we have shown is mod h of e power j omega, and the phase, if you see, h of e power j omega is h of e power j omega mod h of e power j omega, which we have sketched here, into e power minus j omega m by 2. Okay, because of this causal shift we have done to make this causal, and this minus pi to pi. Okay, and what we have said is the in terms of design specifications. Okay, this is one specification, that is stop band minus omega s. Okay, the other specification is this, that is omega p and omega s. Okay, so this omega p to omega s, this is referred to as transition band. Okay, so this is transition band. So you can see that from here to here, okay, it is moving from, okay, this is the region where we are transiting from stop band to like pass band to stop band transition. Okay, as we said, this is proportional to the width of the main lobe. Okay, that is 4 pi by m plus 1 here for rectangular window. Okay, we will discuss this in more detail because as you can see in the convolution, okay, the drop or the rise of the transition band or the width of the transition band roughly depends upon the width of this. Okay, that means it will be keep till there is a overlap with respect to main lobe to the frequency response. Here it is here in the pass band. When this overlap of this stops decreasing with the main like with the pass band and goes to stop band, then it becomes the like stop band. Okay, so it is proportional to this. Whereas the oscillations in the pass band and the main band, like whereas, okay, so whereas, okay, delta P comma delta S. So here you can see that in digital domain, in discrete spectrum, okay, how do we define the transition band? This is equal to WS minus WP. Okay, it is roughly in fact is equal to 4 pi by m plus 1. Okay, so please note that. Okay, so this is WS minus WP is equal to 4 pi by m plus 1 because as I said, this depends upon the width of the main lobe. Whereas delta S and okay, delta S and delta P and delta S, that is attenuations, depends upon what? Depends on height of the side lobes. Of what? Of W e power j omega, window function. Okay, so please note this. Okay, the where this is one important aspect, that is the pass band transition depends upon the width and then the height of the side lobes, which is another design parameters. WS and WP, these determine the height of the side lobe. These are determined by the height of side lobes because see, if you see here, these side lobes are having higher heights compared to main lobe. Okay, main lobe and side lobes are very like, because based on the m, these side lobe heights and main lobe widths can be varying. Okay, so if these are of higher heights, then what will happen? Oscillations will be more, and hence delta S and delta P will be high. Okay, so these are proportional to, so that implies, okay, let me write this here not to overlap with respect to this discussion. Okay, so let me write that implies WS minus WP is equal to 4 pi by m plus 1. Okay, this is coming from 1. Okay, this whole thing is because of discussion 1, and here now this implies delta P comma delta S, we will see particularly are proportional to, okay, height of height of side lobes. Side lobe height. Relative to, so side lobe height means the side lobe height relative to the main lobe height. Okay, right. Okay, so now let us see. This is for all the discussion that we had so far is for the discrete filter. But as I said, usually the specifications are given for the uh, continuous time for a transform domain, in the continuous time for a transform domain. Okay, these are all for discrete filter or digital filter. Okay, for analog filter, Okay, usually the specifications are given for the analog filter. For analog filter, see how do they give specification? Say in the input signal xc of t, fine, we wish to pass up to omega c, okay, some frequencies, while sampling frequency is omega s. Okay, this is how the problem statement will be. And we may allow, okay, delta s ripples in stop band and delta p in pass band. Okay, this is how the usual description of the problem or the filter will be. That means what they are conveying is based on like in the frequency domain of this filter, we wish to design for xc of t device input. Okay, they should have a system here h of t. Okay, and this system y of t anyway output. So the system h of t should have a frequency response that ideally should pass fine minus omega c to omega c. Okay, so this is the specification they have given, and they allow the ripples. Okay, that means they allow. So you can have something like this. That means they allow attenuation of delta p in pass band, sorry, delta s in stop band, and an attenuation of delta s delta p, 1 plus or minus delta p in the pass band. That is what is usually specified, okay, in the question, right? And this is what h of j omega for the filter in continuous time filter. Okay, so these ripples may be oscillating nature like this, or maybe some monotonic nature like this. Okay, that means based on the design of the filter, we may have this kind of ripples, or we may have this kind of slowly approaching like to the pass band and then to stop band. And in this case, the like this is referred to as this. Okay, this will define the pass band cut off frequencies or sub frequencies, that is omega p and omega s. Okay, instead of giving omega c, okay, they may give omega s and omega p. Okay, they can give either. They can give omega s and omega p and ask like we may take omega c, or omega c if they give, we can keep omega p and omega s around. Okay, this is how the specifications of practical filter will be. Okay, so now let us see how to make a conversion. Okay, so let us take a small example to conclude this discussion. Okay, and understand how the transformation of the frequency specifications can happen from continuous time domain to discrete time domain. Okay, let us take a problem. Let the specifications for continuous time filter or analog filter be okay. So yeah, 0 less than or equal to omega b pass band given by, okay, they have given the pass band here equal to 2 pi into 2000 Hz Okay, so they have given passband, so that is omega p, passband cutoff frequency is 2000 into 2 pi. Okay, so fp is equal to 2000. That's what 2000 Hz. Oh, this is one thing they have given. And stop band is 2 pi 3000. Okay, the stop band is above 3000, greater than or equal to 3000. Okay, so this is what is, that is omega s is equal to 3000 into 2 pi. And the attenuations in pass band is h of e power, sorry, h of j omega here, continuous time filter j omega in pass band has to be less than or equal to 1 plus or minus, okay, 1 plus or minus 0.01. This implies what? Delta P is given as 0.01. Okay, and mod here h of e power h of j omega in stop band is less than or equal to 0.001. That implies delta S is given as 0.001. Okay, so these are the specifications given. So we have all the 4 specifications. Okay, so omega p specifications given are, so omega p, okay, delta p, omega s, and delta s. Okay, specifications of n-log filter. Okay, now see, if you want to now find the specifications of discrete filter, let us find the specifications of the discrete time filter. Okay, so what do we know the relation between discrete time filter and continuous time filter? See, mainly what will happen is transformation of variable omega to small omega. So what is the relation we have between small omega and capital omega? Capital omega into time. They have also given the problem that, okay, the sampling time Ts is given as 10 power minus 4 seconds. Okay, or Fs is equal to, okay, 10 kilohertz. Okay, or in omega s is equal to 2 pi into 10 kilohertz. Okay, this is what also is given in the question. Okay, so given these details, now let us see, okay, how do we see, how to first, what I suggest is you can sketch the spectrum in continuous time and then you can sketch the spectrum in discrete time. Okay, so let us see now the spectrum in the continuous time. Let me use some colors. Okay, so let me sketch 0, and this is, say for example, the filter in continuous time. I'm just scaling it, say minus 2 pi into 2000. Okay, 2000 into 2 pi. Okay, now the question what I'm plotting here is omega axis, and hence see, if I sample it in the to get the discrete signal with fs equal to 10 kilohertz, where do you think it repeats? It repeats at 10 kilohertz. So this is 2, 4, 6, 8, and 10. Okay, so it repeats again here, right? And this is, say, this is roughly 5 kilohertz. Fine. Is this 5? 2, 4, sorry, 2, 4. Oh, this is 5. Okay, this is 5 kilohertz. Okay, this is 5 kilohertz. Okay, and even this side you can consider 5 kilohertz, and then this is 4 6 8. So from here the again the next spectrum goes. Okay, so now what, see, if we take only, see, when we sample, we know that this what I have plotted here is x s of j omega sample spectrum, because from the sample spectrum only we get, okay, x of e power j omega later. Okay, from the sample spectrum we get x of e power j omega. So, and after sampling, which is the region I should consider, is only from minus like omega fs by 2 to omega fs by 2, right? So I take the region of only one period in the excess of e power j omega, as you know, because this is itself is self-contained. So this is now minus omega s by 2 to omega s by 2. Okay, this is the region that will give us, okay, this is the region, okay, we, when we normalize with respect to this omega equal to omega by t, what we get is in the time domain, that is in the discrete time domain. Okay, now let me sketch the discrete time spectrum. Fine. So 0, now this axis is small omega axis, please note that, and this is equal to capital omega into t, that is by, okay, 10 into, or like 10 power 4. Okay, and hence, see, this 10 power 4, this will become this is 2 pi by 10. Okay, 4 pi by 10, sorry. Okay, this is 4 pi by 10. Let me sketch with some thick color. This is 4 pi by 10. Okay, and this is minus 4 pi by 10. Okay, right? Because this is 4 pi. You can see that when I can make this conversion, omega equal to omega by 10 power into 10 power 4, what I get is this. Okay, so minus, and then it goes up to, say, where 2 4, yeah, I think it's fine, up to, sorry, this is up to here only. Okay, this is omega s by 2. Okay, fine. Okay, very good. Okay, so now you can see that this is right up to here, minus pi and pi. Okay, so you can see that the magnitude, the height, we can scale it by 1 by t. I am just leaving the magnitude of the spectrum because that's not very important for us, but you can see that this is the frequency response. So now, given this transformation, what are the specifications of in the frequency discrete domain? Okay, this implies that this simply omega p, omega s, okay, and the attenuations doesn't change because they modulate by same amount. So we write delta p and delta s. Okay, whereas where you have omega p is equal to p into t, and similarly omega s is equal to omega s into capital T, right? So the sampling time or the sampling period or or the frequency will determine the transformation from the specifications of the analog filter to digital filter. Okay, that's the only important factor, and remaining all directly follows. Okay, so this is the digital filter we wish to design. This is the ideal desired filter, and based on the practical specifications, we have delta P and delta S for us. Okay, for the design. We will see in the next class. Okay, so how a different windowing functions will affect the delta P and delta S. We'll see, can I meet the given delta P and delta S by a rectangular window of what? Like how many samples should I take? Oh, now say if I take m equal to 10, can we meet delta P and delta S? Or should I take m equal to 20 for meeting them, and so on. Similarly, is there any role of the like the window function? Should it be always rectangular window or any other window that we truncate in the time domain? Okay, so for making this, okay, this selection of the frequent, like the h of n happen from hd of n. Now we see these characteristics of window and its influence on delta P, delta S in the next class. Thank you.